Hello everyone, my name is Nikola Besinovic from Delft University of Technology. Today I'll be talking about mathematical modeling for tackling COVID-19 in public transport networks. So we are all experiencing, no matter where in the world that we are living, consequences of COVID-19, mainly being physical distancing, and that has significant impacts on public transport and railways worldwide. First, we see reductions in passenger demand, which at the worst period was up to 90% drop, and we see certain slow recovery, but then dropping again in the second wave, and still not sure how much time we need to recover. And then we see restriction in train capacity in numbers of seats, and we see estimates anywhere from 20 to 50%. So we can ask ourselves very important questions. One being, what is the transport capacity of our system under physical distancing? And then how to redesign rail services to accommodate as much as possible the existing demand. To answer these questions, looked into capacity assessment modeling and looked into designing network timetables. So when it comes to passenger assignment models, most of them focus on normal conditions, and such extreme situations that we have of overcapacity are rarely under scope. So what we basically want to do for given planned timetable, origin destination, demand matrix, and new limited train capacity, want to find the maximum number of passengers that can be transported. So we model our network in 3 layers, including infrastructure, then trains are running on the given infrastructure, and passengers using these train services. And we assume that our passengers are routed via shortest paths. So if we take one origin and destination, our train passengers could take one or multiple routes, and we can identify the share that they are using each of the paths, and each path is clearly associated with the cost, where the higher cost represents the shorter route. So the constraints, so basically we have these decisions and parameters for each OD pair, and for each path between, for each path of OD pairs. So for these hold up for certain constraints, basically trains are modeled using arc-based constraints, passenger using path-based, and they need to satisfy train capacity and infrastructure link capacity. What you may already recognize that this may lead in an extremely large number of potential paths, and in order to solve this problem, we introduced a column generation approach to efficiently insert only the relevant paths for passengers and not to consider them all at once. So we considered an experimental setup of a Dutch railway network where we looked at 5 variants of demand size, being 100% representing normal conditions, and 4 restricted, ranging from 5% to 75% of demand. And it comes to train capacity, looked at the normal and restricted of 1/4 of the designed capacity. Report transported demand and link utilization. So looking at a number of transported passengers, proposed it against a given demand share being 5 up to 100, and we present number of passengers that are actually using. And what is interesting to see that only with a 5% demand share would be able to transport complete demand. But as we increase, we we don't manage to transport more and more of demand, and once demand would fully recover, would be able to transport only about 50% of the actual demand. And yeah, 50% passengers would not be able to travel. Looking at link utilization, we show the color represents how each link is utilized, red meaning fully utilized. And we see that for COVID-19, even though we have 50% less passengers, many more links are actually congested. And what we don't show here is that even about 70% of trains will be fully utilized on at least one section of their journey. So we are clear that we have serious transport capacity issues. So it brings us to the second question, is how we can redesign railway services to satisfy demand as much as possible. So we go to network timetabling. So to get everyone on the same page, where we put our focus on is periodic timetabling, and which means basically we schedule our services within a certain cycle time and then repeat this timetable over the day. So for example, if you have a train running at 9:02, it will be running at 10:02, 11:02, and the same throughout the day. Another concept we need is timetable stability, and we define it as availability of the periodic timetable to return to its schedule from disturbance. And what we consider as input for our periodic timetabling is a target line plan, which consists of ideal train lines, which include origins, destinations, stops, and frequencies, and is basically created based on the expected passenger demand. And one example of a target line plan can be using existing demand with existing train lines, but then it would result with much higher frequencies due to limited seat capacity resulting from COVID-19. So imagine that for a given target line plan, and very many train services will not be able to be scheduled. Another important concept we want to introduce is minimal cycle time, which basically represents the smallest time duration in which all events are feasible in the given period. So for example, if we consider one line and 4 trains equally spread, or with regular services of 15 minutes, we compute our lambda by bringing them as closest together to satisfy their headways, and we use this as we can consider it as a stability measure, and we can translate this concept from a line to a network. So we can call our minimal cycle time as a network level stability measure. So we can say that timetable is stable if lambda is smaller than t and unstable or critical otherwise. So we can take our target line plan, schedule the cycle time, want to compute a stable timetable that satisfies the most demand. So how we model it? We take a periodic event activity network, where periodic events represent arrival and departures, and they are associated with the corresponding arrival departure times called pi, and we have our activities being running, dwelling, turning, and the regularity. And we have regularity for train lines that have frequency 2 and higher. So we want to have them equally spread within the period T. So our model for minimal cycle time is basically minimization of the cycle, and we have to satisfy constraints on our running, dwell, and headway activities within certain lower and upper bounds. And we want our trains be regularly spread throughout the period. And we consider certain relaxation measures, given that not all trains can be scheduled. So one is relaxation on a line plan, and the other relaxing timetable design parameters. So what we can do is we relax or reduce train line frequency by removing certain services, and we can also relax regularity constraints and relax running time by adding more time supplement to allow for certain extended running. And we have to solve this problem. We have an iterative heuristic that we use to resolve instability. So what we do, we take the line plan, we solve fast lambda, check if it's stable or not. If it's not, we relax some of the measures and resolve it again. And we do it iteratively until we get a stable solution. So we tested our model on a part of the Dutch network. We used various scenarios where we varied number of train lines, frequencies, train services, and we compared two variants, one where we relaxed only train services and the other one where we relaxed on all three measures. And we report a number of scheduled train services. So for a given target line plan on X axis, we report the number of train services that are actually being scheduled. We can see that in the beginning, for smaller numbers, up to 42, managed to schedule all train services for both variants M1 and M123. But then afterwards, some are being cancelled, and we see some sort of a convergence effect. And actually, for all these restricted solutions, we see that when we apply all three variants, all three relaxation measures, we were able to schedule more trains than when we relax only on the line plan. So we can see that for having some relaxations on design parameters, we could have more trains scheduled, which is quite interesting to see. And why we don't see a nice convergence is basically because we have some randomness in picking which train services to remove in our heuristic. So that's something we could look in the future. And that brings us to the conclusions. So what I have are three main takeaways for you. One, that we can efficiently use advanced mathematical models and algorithms for addressing highly pressing present worldwide challenges that we experience. Second, we can evaluate impacts and identify bottlenecks in the capacity of railway networks, and we can redesign the railway services efficiently to suit better the new conditions. And that's not all that we are doing. We are looking further toward modeling for integrating assessment of capacity and timetable redesign, but we can also look into demand prediction and also impacts of new technologies like on-demand services, and looking more into real-time if we can optimally space people within our vehicles. That will be all, and I would like to thank you for your attention.